Hello, everybody. Let us start our discussion today. And as always, we'll pick up from where we left last time. Let me remind you, in a region of space where you are trying to calculate the gravitational field, if there in that region where you are trying to calculate there is no matter density, so in a region of space where if I want to calculate the gravitational field, I have to put a test mass over there, but there is nothing else, no energy or no density, no mass apart from the test mass. And I say any mass, and in special relativity, we know that mass and energy are equivalent. So, this is the region of space that we are interested in, or we were interested in last time. In such a region of space, if I want to write down an equation which gives me the gravitational field, so that in Newtonian mechanics or Newtonian gravity, that tells me this equation is a Laplace equation of the potential phi. And it's a Laplace equation, so right hand side of this is 0. So this is this gives me the gravitational field. This is the potential of the gravitational field. And we kind of argued that in general relativity, so let me write just GTR, general theory of relativity, this we kind of argued will be replaced by this equation where G alpha beta is the Einstein's tensor. And remember, G alpha beta contains the metric, the first derivatives of the metric, and the second derivative of the metric. And also, this is important, that's a tensor equation. So this is a law written in a covariant form. That is, all the equations in a law, if is expressed by tensor equations, we call that law written in a covariant form, because then we can do a general coordinate transformation and write down the equations for that physical law in any other reference frame. So this was our case for a region of space which is free of any mass or energy. What happens if I consider a region of space which has a mass or energy? This we have to address if we really want to write down a theory for the gravity. Now, how am I express the mass or energy is a question. And in Newtonian gravity, we know already how to express this. So, in Newtonian gravity, I have almost the same equation, but now it is not a Laplace equation, it's a Poisson equation, where in the right hand side I have I also have a capital G, which is not anything to do with, has nothing to do with the Einstein tensor, but it's just the gravitational constant. But I have this is mass density, which is mass per unit volume. So this is what I have for the Newtonian gravity, where in the space there is some mass or energy, and the presence of the mass or energy is given by this quantity, which I call the mass density. Now, obviously, the question now is, how do I write an equivalent relation or equivalent equation, how to write the equivalent relation when I write it in terms of a covariant form in a tensor equation as like general relativity. General theory of relativity. So that is the question that we'll kind of try to answer today. Now, this is a first principle. Nobody told Newton, or you cannot derive the Poisson equation for gravity. It is just if you write down the Poisson equation in this particular way, you can explain the orbits of the planet very well. So that's why it works. Similarly, we can argue, taking clue from Newtonian gravity, that what should be the equation that will tell us how things change once I have presence of mass and energy, but no one can actually derive such an equation. So expected form of this equation, well, we already know what happens if there is no mass and energy. So it's expected that it will have a form of some constant, say kappa, time second rank symmetric tensor. Remember that G alpha beta is symmetric. So the right hand side has no other choice. Kappa can be any constant. So this should be a universal constant. So we are in search for this second rank tensor. What information would it have? Let us guess. Well, this must be given by the mass or energy density. But is that all? Maybe something else which I need to write this down. But let's skip that for the time being because we'll see what is actually required shortly. But roughly speaking, at least it will have the mass or the energy density term. Now, we realize one more thing. The other thing we realize is that we have already started to take a more average description of both the space-time and the mass energy. So this equation is a kind of an average description which is to say that this quantity in the left hand side has a value at all values of the coordinates. So this I can call like a field. And if that is a field, the right hand side also has to be a field. There is equal to sign sitting in between, which means here as we see that these are density, these are also averaged over volumes. And as you can guess, when now we are talking about things in terms of four-dimensional space, and we really does not distinguish apart from some sign conventions between space and time, this volume can be a space-time volume. Okay, so now it is clear that this equation, and this equation is something that we will call the Einstein's equation, because this is what will give the real meaning of gravity. we have not write it down properly, but we will call this Einstein equation. So this equation gives an average description of things. So what do I mean by average description? I mean that now I do not look at individual particles and don't ask the question what is their mass, what is their momentum, what is their energy, but I look at many such particles and ask the question what is the average energy of this particle, what is the average momentum of these particles, etc. Or can be number density of these particles. This concept is very important, and we have already seen with one example papers that you have read that we really need to treat the individual particles. Here we cannot, like for example, in a rigid body dynamics, though we have in a rigid body like a block of wood, I have some 10 to the 30 particles, but I don't have degrees of freedom equals 3 into 10 to the 30. Rather, I have degrees of freedom equals only 6, where we say that, okay, it's a rigid body. The distance between the particles doesn't change. So I can just specify the position of the center of mass and the orientation of the body with respect to the center of mass. That requires only 6 coordinates, 3 for the position of the center of mass and 3 for the rotation about the center of mass. Unfortunately, as we have seen in with the description in the special relativity, that such type of considerations, approximations as rigid body does not hold true when you come to relativistic motions. What now you need to really do is to consider the motion of each particle separately. And that's 10 to the 30 particles in case of the block of the wood, which obviously you cannot do. So what you say is, okay, I cannot track each and every particle, but I can give you a description of what is the average motion of a bulk of this particle. And that is what we call a fluid description of the system. And let me just, though we have gone through the fluid mechanics once in this course, let me just remind you of fluids and particularly fluid equations. Remember that when we talk about a fluid, we have a flow. Think of it's a flow of water and don't consider anything relativistic for the time being. And it's going through a pipe which may look of this funny shape. And we consider a small volume which we call a fluid element. This volume has macroscopic attributes. These are the attributes which one cannot give to a particle, but these are those volume average attributes. These are like density, pressure, temperature, and many more. This will serve for us. Even we will not need temperature for the time being. But anyway, so these are the macroscopic attributes. It also, I can define a velocity of this, which is the net velocity of the entire fluid element, which means that if I average over all the velocities of the particle, this is the velocity which is left over. It may be that individual particles are moving around, but on a large time they doesn't go anywhere. In that case, this velocity will be 0. Like if I am sitting in a closed room, all the air molecules are going around very fast in different directions, but their bulk motion is 0 because they cannot go out of the room. Now, remember that we can write down the fluid equations, and the continuity equation reads the continuity equation tells you that you cannot create or destroy a fluid particle, and that equation is d rho dt plus divergence of rho v equals 0. And if you really want to bring in special relativity here and say, okay, I am looking at this fluid element from a reference frame. In that reference frame, this fluid element is moving very fast. So I can put in a gamma over here. But it's not, let me put this gamma with a different color, because that is what you not saw in your original fluid mechanics lectures. And then I have Euler equation if it is a perfect fluid, and I will even not bother to write down the Euler equation. So this is for perfect fluid, because this is what I am going to give you as a homework shortly. What is a perfect fluid? Well, I don't have any viscosity. So no viscosity implies no shear stress. And also, for a perfect fluid, pressure is isotropic. Remember the Pascal's law that we all read in our childhood in school days, which means if I consider a small volume in this fluid, and I can, because I have this surface, and if I have a force perpendicular to this surface, I can define a pressure here, which is, if I call this surface as x, z, and this is say y, don't bother about the right hand coordinate system for the time being. This is just a demonstration. So the force along y, divided by the area along xz, this we call the pressure along y. And so that will be, this is one pressure, but I have three of them because I can have a pressure which is because of force along this direction, and then one which is because of force along this direction, and all these are same. So that's what I call a perfect fluid. And Euler equation, which you should write down to fill in the gap here, is true for such a perfect fluid. And it looks like that we need to do a fluid dynamical description of the system, and we need to figure out a quantity which will sit in the right hand side of the Einstein equation. That quantity should quantify the energy density, at least it should quantify the energy density or the matter density, the kind of equivalent apart from a c-square factor. And that's what is our endeavor now. The first thing we need to do to define a density is to define a volume. So how to define? And we talk about a three-dimensional volume. We are living in 4D manifold. So this is the question we have to first answer. But to answer this, we will take an example first. And I call it a lesser example because it is from a lesser dimension. So this is for a 2D volume. A 2D volume we call a surface embedded. So this is essentially called embedded in a 3D space. This is our usual thing. Basically, what we are asking is, what is the meaning of this? This is a more kind of abstract way of saying that I have a volume, and let us say that when I talk about a volume, it's a differential volume, dV, enclosed by a surface. Okay, so that is what I have, and I asked the question, how do I represent such a surface? Why do I want to do that? Well, if I can understand in this more familiar example, that surface is this surface is essentially this 2D surface which is in the 3D space. Maybe then I will be able to carry it forward to write down what does a 3D surface, a 3D, it's called a hypersurface, looks like in a 4-dimensional manifold. How can I represent it there? Okay. Now, how do I define a surface? Well, one surface that we are all familiar with is a equipotential surface, and such a surface is there are many such surfaces around the Earth. For example, Earth is, if you assume it to be a spherical body, there are many such spherical surfaces around Earth, and that surface encloses Earth inside it, and that's the physical scenario that we are talking about. And if you think a little bit about it, you see that we are trying to get to a energy density or matter density type of thing, and the description that just the example that I have just gave you has some type of smell of the divergence theorem, where that surface we are talking about, spherical surface, encloses the mass inside it. So one can define the density of mass using such a surface. Anyway, so how do I define a surface? Well, it's a thing where a scalar quantity, in the Newtonian example of gravity, the scalar quantity we call phi, the potential, is constant. So any such surface embedded in higher dimension, so it's a when you think about a less than one dimensional thing in a n dimensional space, so that's called a hypersurface. So this is a hypersurface we are talking about. This hypersurface, any such hypersurface, can be explained, can be written by any scalar function. It's not potential. It can be potential. It's not necessarily potential. Any scalar function. Remember that a scalar is can be given by a function, a single function. For a vector, you need 4 in 4 dimension, and this is a function of all the coordinates. And this equation for the surface is that this equals constant. For the example that we talked about, the sphere, it is x square plus y square plus z square equals to r square. That's the equation. Now, if this is my equation, we can calculate a differential change of the surface. This we have done before, but let me do it again. So this I can write in this particular example, and then plus dy plus dz, but I know we are quite familiar now with this notation, which is nothing but a one form which we have talked about many times earlier with this vector dx, the dot product between these two, which I can also write as kind of d phi l and dx. L is something that goes from 1 to 3. It's a Roman index, it's not a Greek index. So this is, as we said, this surface is not an infinitesimal surface. It goes to infinity. It can go to very large distances. But the whole point is that the surface is given by one form. particularly this one. So what I can do is, which this gives me a clue to how to define a surface. I can define a surface, and all of us know that what is the direction of this one form. You see, if I consider a surface such an embedded surface, remember that this surface has a dimensionality which is one less compared to the dimension of the manifold, which means I can go off the surface in the one extra dimension that I have. So this surface is n minus 1 dimensional, and the other dimension is, say, of the surface. So total is n dimensional manifold. And these dxls are tangent vectors. So they live in a tangent vector space. So if I point any point here, so they are all in this and the tangent to the surface. And this dot product is telling you that that vector is normal. So the one form, if you wish, within quotes, the direction of the one form is kind of the normal to the surface. So that's the direction of the surface changes. So now, once I know all these, so I know that I can describe an infinitesimal surface now. What are the properties of such a surface have? It has an area. So let's call that dA. So it has an area dA. What else does it have? This area can be oriented any way in your n-dimensional manifold. This n minus 1 dimensional area can be oriented in any way in your n-dimensional manifold. To specify a particular area, I need to give you the direction to the normal, and that we just have seen is given by a one form. Why don't you take the unit one form along this direction? Okay. So I take a unit one form along this direction, which means that its norm is unity. Not necessarily a unit vector, by the way. It's not necessarily a coordinate unit vector. It's just that its norm is unity. So it's a unit one form. And I have the area of that differential element. So this will define an infinitesimal area for me. Only thing I need to remember is that, for example, here, if I consider I am living in an XYZ plane and the direction of the normal is Z, then the area has the coordinates x and y. Well, it can be, as I should mention it clearly here, it's not necessary that this area can be only xy or yz or zx. It can be some combinations of them also. This is just an example, easy example we are picking up here. So n alpha in that case will be at 0, 0, 1 and whatever dA is. But dA is, if it is a differential area element, it can be dx and dy now only. So whichever are 0 here, only in those differentials has to come there, because this is example of an example of an example. This is because this directions are on the surface and this direction is off the surface. Together they prescribe all the directions possible, if you wish. Now that's the 2D example, and now we can easily write down the 3D example. So a 3D, I call it hypersurface now. In 4D space-time, that is the manifold that we are interested in. How will we write it? So let's write it in the following way. We call it n now mu because it can go 0, 1, 2, 3, and d omega. You may ask me why I am not writing d mu. It will be clear shortly because I will take up two examples. In one case, I choose n mu, which is normal to the surface, to be this. Then this quantity becomes dx, dy, dz, the usual spatial volume or in elementary spatial volume. In the other case, if I choose this to be one of the coordinates, it doesn't matter which one, any one of this. Now you see, okay, so first let me step back one step and let's see what I have written down here. So this entire thing, if I want to write, it has 4 components as expected, and I'm just writing it as a column vector. It really doesn't matter. I should have written down it as a row vector, but I don't have so much space in the horizontal direction. It really doesn't matter. I have 4 components which I have clubbed here together. First component is dx, dy, dz. The rest are 0 because n mu, the rest are 0. In this case, what I will get is the first one will be 0 now. Second one, this will be c dt because that is what is dx 0. And then I will have dy dz. And then the rest are again 0. And that's why I call it d omega, because then you remember that it is not really a volume, it is a hypervolume or hypersurface, because I can have a kind of spatial area here multiplied by c dt. That also gives me a 4D volume, a 3D volume in 4D spacetime. All right. So this is the denominator of when I want to calculate or want to formulate something which looks like the density, energy density or matter density. Let us remind ourselves of the numerator, which is energy. What is a form of energy in special relativity? What is energy in special relativity? Energy is just the 0th component of the energy 4 vector. So if I write the energy 4 vector as epsilon and mu, so this is my energy 4 vector. The 0th component is energy, and the moment and the spatial components are c times p, where if you remember, p is nothing but m v 3 velocities gamma, and e is nothing but mc square gamma. So this is in an arbitrary frame, in a frame where the particle have a velocity v. So we are looking at a particle and trying to guess what is its energy and momentum. If the particle has a velocity v instantaneously in that reference frame, this is the energy and the momentum of the particle. In a frame where the particle is at rest, momentum is obviously 0 and the energy is mc square. So this is all that we know from special relativity. If you are not familiar with the energy 4 vector, you are familiar with the momentum 4 vector, I am absolutely sure, which is E by C and the 3 momentum. and you just divide this by or multiply this by c, you get the energy 4 momentum. Energy 4 vector. It is just customary way of writing it. Okay, now that we know how to write energy, what is energy? So energy is, remember, it's not a vector or a scalar, it's a component of a vector. So if I go to a different reference frame, it doesn't transfer like a scalar. So there is a gamma factor appearing over there. It doesn't transfer like a scalar. You have to transfer the entire thing as the energy, as the momentum, and then you have to ask the question that what it is that you are looking at. Now let us come to the fluid description. So we come to a description of a relativistic fluid. So what is the description that we want to talk about? Well, I have this volume, say this box, and in this box, so there are so many particles, 10 to the whatever number, and they are going around. Each of these particles has a certain velocity, and they're hitting the walls of the block, so there can be pressure. The particles has energy, so there can be density. So which means that inside, for this block, we can define certain things. So we can define, say, energy density, and we'll call everything in terms of energy density because, so we'll come to momentum density, mass density later. But the reason we want to talk about energy density is that in relative special relativity told us that mass and energy are equivalent. So if I just talk about energy density, the mass density will be carried forward. I mean, one is off by the other by a factor of c square. C is a constant. We know its value. There is no harm. So we want to define energy density. So how will I define this? It will be the average energy in the volume. I can define this entire thing can be going in a given direction. So just imagine that you first look at this box. This box really has rigid walls, so the particles cannot go outside. This is just for your imagination. This is not a requirement. So the box has rigid walls, particles cannot go anywhere, and you have kept the box at rest and you are looking at the motion of the particles. At this point, the total average velocity of the box is 0, right? So the momentum of the box is also 0. So similarly, I can define a momentum density or a momentum averaged over the block just like average energy in the volume. Now I have an average momentum of the block, and I can combine these two to define an epsilon, which will be the epsilon 4 vector. This epsilon 4 vector doesn't give you momentum and energy of individual particles, but of the entire block. So that's the 4 vector for the fluid element, if you wish. So this is my fluid element. So this epsilon 4 vector, as like before, I will have an energy, and I will have P times C. P is the 3 momentum. And remember that this P you can also write as mv gamma. All the thing that we have written down here we'll hold just to just remember that this epsilon was of a single particle. Now what I am writing down is of the fluid element. Okay, all right. If I want to write this now in a differential form, a differential of 4 energy of the fluid element. Okay, so which is d epsilon mu. Okay, what will this be? So let's see what is the, how can I write this down? This I can write as the sum density times differential volume element. Now we already know how to write down a volume element. So this I can, so this will be a one form, unit one form. So let's call this n nu and d omega. Now this d omega, remember that it should have components only perpendicular to n nu. So what type of object this can be? This has to be an object which will contract this nu and it will have an extra mu element. So this has to be of this form. So we call it T mu nu. So this is a tensor of the form 2, 0, which gives energy per unit volume. So energy density. So it's an energy tensor. It will be probably more because you can imagine that only the 0th part of this is energy, E mu, epsilon mu is energy. The rest 3 are momentum. So it's better call this energy momentum density, and this we call the energy momentum tensor. Let's have a guess at its components. So how many components will it have? 4 into 4 components. So let's have a guess at its components. So components of the energy momentum tensor. So let me write it. It's a rank 2 matrix, sorry, rank 2 tensor. So one can write it as a form of a 2 by 2 matrix. So what are these? So let's have a look. So first let us choose the surface. Remember that when you talk about all these things, when you talked about this volume here, I can choose a surface and ask the question that something happening through that surface. Here also I can choose a volume. So let's choose the volume to be this to be the first case we discussed earlier, which is Okay. So the first component is just the spatial volume element and the rest are 0. Now if I look at the equation I have here, this equation, then it's telling you that d epsilon mu is t mu, and mu is supposed to be 0, so this is 0. That is a component that I have written down. So this we have chosen to be n0 essentially. And then let's call this dv. So dv is the spatial volume, normal spatial volume. So if now, so now this is a, there are 4 components of this. Mu can be 0, 1, 2, 3. So if mu equals to 0, I have d epsilon 0, which is nothing but dE, and that is equals to mu equals to 0, t00 dV. So immediately I see that t00 is nothing but dE by dV. So which is energy per unit volume or energy density. So this place is for energy density. What about mu equals 1? Well, you don't need really separately to do for 1, 2 and 3. I can just write mu equals L, where L stands for any of the 3 spatial coordinates. So then I will get d epsilon L equals dL0 dV. And d epsilon L, if you remember, is nothing but C times P dP. So this is dP L dV. So this region is C times momentum density. Now I will not prove it for you, but you can check that it's a symmetric tensor. So this part and this part will be same. And if you, this also I leave for you. If you calculate this part, this will come out to be stress, which is a matrix where you have pressure in the diagonal elements and the off diagonal elements are the stresses. So let's call this sigma. I will not write them down explicitly. You can fill it up. And how do you get that? What I have to do is, so let me do one for you. So let us say that instead of taking this surface, now let's choose the surface to be, in this case it's a hypersurface, so and nu to be say 0, 1, 0, 0. So my equation d epsilon mu will now be t mu 1. What is dv? This also we did last time, so it will be c dt and dy dz, which let us write ayz. So that is the area in the yz plane, elementary area in the yz plane. Now what is d epsilon mu? This is c times d. So let us consider only the spatial components. So that will be dPL, and let us bring the differentials in this side. So this is C dPL dt, and then I have 1 by dA yz, and that will be equals C T mu 1. So I should not write mu here, I should write L. So TL1. So again, if I choose now L equals also 1, what I have here is the T11 component. C cancels out from the both side. dP1 dt is nothing but the force. Which direction is the force? The force is along one direction, which is x direction, and the area is along the yz direction. So this, you will agree, is the pressure along x. So that is what I wrote here, which is the 1 component here. Okay, so I will request you to check for the rest of the components, and you will see soon once you look for all of them. This is the form that I get for the T mu nu. Okay, so we are almost at the end of the lecture today. What we will do now is to consider two examples, which are the two most, or the generalization. The second example is the only example that we look at in this course. So let's do that. So let's first consider a case. So this is called dust. So this is a type of fluid. You can consider it in two ways. One, you can say that it does not collide with anything, which will make its pressure to be zero, because pressure is essentially a result of collision. On the other hand, the easiest way to think about such a fluid called dust is that there are particles, and this is the box is at rest. Number density of the particle is n, and mass of each is capital M, small m. The particles are all at rest. This is in the rest case where the box is at rest. In case the box moves, obviously all the particles will start to move with the same velocity. Okay, so what is the energy momentum tensor for this? So let's look at the components. So what all I need to know are what is the energy density, I'm trying to write it down in the frame where all the particles and the box is at rest. Well, it is very simple here. In this reference frame particularly, the energy density in this reference frame is mass times n, which gives you the density of number density. So mass times n gives you the mass density times c square, and that's it. I don't need anything else. mc square is the energy of each particle at rest, and there are n such particles per unit volume, so energy per unit volume is mnc square. If I now want to write this down, not in the frame where it is at rest, but where it is moving with a certain velocity, then you can guess what I have to do. I have to just multiply this by gamma. That is the reference frame where the box is moving with a velocity v. So gamma is 1 by root over 1 minus v square by c square. What is the momentum density? Okay, so I'll come back to the factor gamma later because otherwise it will create confusion. What we said is correct, but we'll come back to it later. So the momentum density in the reference frame where the box is at rest is obviously 0. And we said that the particles does not collide, so all the pressure and the stress are all 0. So which means this is a energy momentum tensor where T00 is mnc square and Tij for I not equals to 0 and j not equals to 0 is all 0. I mean, I could have written mu nu also, it doesn't matter. I mean, all the other components are 0. And mass time number density is nothing but the mass density. So this is rho c square. Rho is nothing but mass per unit volume. One thing you should remember is that volume does change as you go to a different reference frame because the direction where the motion is, the volume, the length gets contracted, so the volume will change by a factor of gamma. So when I write this rho as mass per unit volume, you should always consider that volume in the reference frame where the box is at rest. So this rho c square is the value of the mass density times c square in the frame where the particle is at rest. You can actually write this in a more interesting and insightful form, and it can be actually motivated and derived into. We don't have time for doing that here. I'll just write the final form, final in the sense that if I write it this way, T alpha beta, this can be written as rho u alpha u beta. And this is for dust in any frame. How do we see it? Well, if I go to the reference frame, so first let's consider u alpha and u beta. So frame where is at rest, u alpha is C0, 0, 0, and so is u beta. It is clear that only alpha equals to beta equals to 0 component will survive. So the only non-zero component here is rho c square, which is exactly what we wanted. But if they have velocities, then it will change. So u alpha and u beta will change. And remember that these are 4 velocities, so it will become c gamma and v gamma. And according to that, your energy momentum tensor will also be different depending on which Lorentz frame you are. What is the velocity of that box in that reference frame? That box is essentially the fluid element. If we consider, instead of dust, we consider the second example, which is of a perfect fluid. And remember that what we called a perfect fluid is something where px is same as py, same as pz, which I call p, and all sigma are 0, so there is no stress. For a perfect fluid, again I'm not going to derive for you, but at least for the rest frame, you can see in the rest uh, when box is at rest. Well, when the box is at rest, it doesn't have any net momentum. So this is bound to be rho c square here, and then p, p, p. So it's diagonal, everything else is 0. But in general, one can write T alpha beta for a perfect fluid as minus G alpha beta times P. You can check if you get back this when in rest. Check this. Okay, so we are almost done. Just so we have got something we call the energy momentum tensor. Let me write it here. And all that we'll do henceforth will require the energy momentum tensor of a perfect fluid. So I can write it this way. The energy momentum tensor has to be a symmetric tensor. I will not go into the deep of what is the reason. But this is a symmetric tensor. The construction here, you can see it's symmetric. So this tensor has things like the energy density, and it looks quite the candidate for the right hand side of the Einstein equation. Is it the candidate? We'll see in the next lecture. But let us look at it from a little different perspective, and we will see that something very sacrosanct about it we will discover shortly. One thing is that this entire thing is parameterized by two functions. One is p and one is rho. But if I have equation of state established, so this is like you are in some type of equilibrium, then I can write p as a function of rho, which means that now if I know rho, I know the p as a function of rho, and I know rho, how rho changes as space time changes, then I have an expression for the energy momentum tensor. So I just need to know how rho changes as the space time changes. So this is for perfect fluid, by the way. This is not in general, of course, but that's what we'll deal with. Now just one thing I will show you and one thing I will let you prove as homework. Let's calculate T alpha beta comma beta. Let's see what it is. And you will immediately understand the power of writing things in this type of covariant language. So what is this? Well, beta is summed over. So I can write this as T alpha 0 del x 0 plus T alpha L del x L. Okay. What is T alpha 0? Well, now I have to choose which component of this I want to look at, because alpha can be 0, 1, 2, and 3. So let's look at this component. So that makes me write this as T00 del x0 plus del 0L del xL. T00 is nothing but c square times rho, so this is c square, and del x0 is c dt, so this is this. del rho del t plus, well, T0L is c times the momentum density. Now, how do I write momentum density? The momentum density, remember the momentum density is momentum times the density of the thing. So it is just del of rho v del x. It's a very bad notation, but you can see what we get in the next line. This is entire thing is what is that in the bracket? It's not, it's just the left hand side of the continuity equation. So this is 0. So you learn that T0 beta comma beta equals 0. And your homework is to look at for these components. So you get the continuity equation out of it already. Your homework is to look at this component. This will also come out to be 0, and this will give you nothing but the Euler equations. The entire fluid mechanics is there in this small box. That's amazing. And this is something will be very useful for us as we will proceed with our discussion in the next class. Thank you.